Good morning, everyone. So today we're gonna be tackling a topic with my members, and before I move on with the main topic, I will state an example. So you're planning a birthday party and you decide to fill up a bunch of balloons with helium the night before. So you live in the Philippines. We live in the Philippines. So where the temperature can vary quite a bit from day to night. So you fill up the balloons in the evening when it's cooler and they look nice and plump. So, however, the next day in the heat of the afternoon, you notice the balloons have expanded and some have even popped. So, our topic for today is gonna be thermodynamics. So, thermodynamics is like the science of heat and energy. So, imagine a balloon again. When you blow it up, thermodynamics helps us understand how the air inside the balloon gets warm, making the balloon stretchy and bouncy. But our focus for today is the ideal gas law. Now, again, what is ideal gas law? So, the ideal gas law is like a magic formula of gases. So, it tells us how the pressure, the volume, and temperature of a bunch of bouncing gas molecules are all connected, helping scientists understand how gases act in different situations. So, just like when you blow up a balloon and it gets bigger and tighter. Now, let's move on to the proper lesson. So, according to the module, an ideal gas is defined as one in which all collisions between atoms or molecules are perfectly flexible and in which there are no intermolecular attractive forces. So, in such a gas, all the internal energy is in the form of kinetic energy, and any change in internal energy is accompanied by a change in temperature. So, as what I've just said earlier, it is perfectly flexible collisions and no attractive forces. So, an ideal gas can be characterized by three state variables. So, one is absolute pressure, which is P, the volume, which is V, and absolute temperature, which is T. So, the relationship between them may be deduced from kinetic theory and is called the ideal gas law. So, the ideal gas law is the equation of state of hypothetical ideal gas. It is a good approximation of the behavior of many gases under many conditions, although it has several limitations. So it was first stated by Benoit Paul, Émile Clapeyron in 1834 as a combination of the empirical Boyle's law, Charles' law, Avogadro's law, and Gay-Lussac's law. So, the behavior of an ideal gas, that is the relationship of pressure, or P, volume V, and temperature T, can be summarized in the ideal gas law, PV equals nRT. So, where N is the number of moles of gas and R is equal to 8.31 joules per mole K, is known as the universal gas constant. Universal gas constant. So, P times V. So, think of P as how much the beach balls push against the wall. So, if you squeeze them in a smaller space, the pressure goes up. So, N, which is the number of moles, this is like counting how many bunches of balls you have. So, R, which is the magic constant, this helps us put everything together. It's like the secret sauce. So the next is the T, which is the temperature. So think of it as how fast the beach balls are moving. So if you heat them up, they bounce around faster. An alternate way to express the ideal gas law is in terms of N, the number of molecules, rather than N, the number of moles. So N, capital letter N, is simply small letter n, multiplied by Avogadro's number. So the ideal gas law can be written as PV equals NKT, or Boltzmann's constant K equals R over NA equals 1.38 times 10 to the power of negative 23 joules per Kelvin. So now Boltzmann's constant K is like a special number that helps us understand how temperature and energy are connected. So it's like saying for every bit of energy, we need to use this much of temperature. So if you want to pull all this together in a simple rule, it's like saying the pressure times the volume is equal to the number of tiny things times Boltzmann's constant times the temperature. So, and that's the cool way to understand how these tiny things behave when they're bouncing around their space. So, and the part in parentheses gives the value for Boltzmann's constant K, which is calculated as the universal gas constant R divided by Avogadro's number, which is Na, and is approximately equal to 1.38 times 10 to the power of negative 23 joules per Kelvin.
So the laws of thermodynamics has a good relationship between the ideal gas law. As explained earlier, ideal gas law uses temperature, volume, and pressure to work. These three state variables vary in usage and affects the laws of thermodynamics, which will be explained later. So thermodynamics involves heat and work, where the two transfers energy and that energy is internal energy. If this occurs, a thermodynamic system follows. Wherein a thermodynamic system includes anything whose thermodynamic properties are of interest. It is embedded in its surroundings or environment. It can exchange heat with and do work on its environment through a boundary, which is the imagined wall that separates the system and the environment. A good example of a thermodynamic system is a gas confined in a piston in a cylinder. If the gas is heated, the energy is added to the gas molecules. We can observe the increase in average temperature or kinetic energy of the molecules by measuring how the temperature of the gas increases. As the gas molecules move faster, they also collide with the piston more often. These increasingly frequent collisions transfer energy to the piston and moves it against an external pressure, increasing the overall volume of the gas. In this example, the gas has done work on the surroundings, which includes the piston and the rest of the universe.
In the first law of thermodynamics, it states that the heat added to a system is equal to the sum of the internal energy plus the external work done by a system. When energy is being transferred, we use the formula delta U is equivalent to heat minus work. When there is zero volume, W is equivalent to 0, which means that delta U is equivalent to Q. Any change in energy is the result of heat transfer, which means that heat is coming in and out. This is called the isovolumetric process. A very good example of this is a bomb calorimeter, which means that combustion occurs within, however, the rigid walls of the container remains the same. This is because only heat transfer occurs and the volume remains the same. When there is no change in temperature, this means that internal energy does not also change because their values are proportional to one another. This means that delta U is equivalent to 0, which leads to Q is equivalent to W. Heat is transferred completely used for work. Let's take a car engine for example. When combustion happens, heat is being converted as energy in order for the car to move. There is no heat transferred. Q is equivalent to 0, which means that delta U is equivalent to negative W. When this happens, internal energy is used only for work. This is when work is being done to surroundings or the surroundings does the work. This is called the adiabatic process, which means there is no heat transfer. We can take an example at the atmosphere. The air masses change due to the different pressures. And if Q is equivalent to 0 and W is also equivalent to 0, This means that there is no heat nor work transferred, which is why we have delta U is equivalent to 0, meaning that there is no change in internal energy. This is called the isolated system. Before we use the formula, let us know how to use the signs first. When heat is being absorbed, it is a positive, but when heat is being lost, it is a negative. When work is being done by a system, it is a positive, but when work is being done in the system by the surroundings, it is considered as a negative. When solving equations, make sure you use the right signs, or else the solution will be incorrect. Let's take for example, 100 joules of work is done on a system while internal energy increases by 74 joules. How much of energy is transferred as heat? Let's rearrange the formula into finding Q. Q is equivalent to delta U plus work. So Q is equivalent to 74 joules plus negative 100 joules because work is being done on a system. So then we get the answer negative 26 joules, which is the equivalent of Q, or the heat being transferred. Since equations will be used a lot in thermodynamics, let us check your reading comprehension by solving the equation given.
We will now discuss the PV diagram. Pressure and volume exhibits a causal relationship, meaning that the change of one variable will cause the change in the other. To understand how pressure directly affects volume and vice versa, let's consider a gas sealed in a container with a tightly fitting yet movable piston as example. If a force is applied, the piston moves down and the gas would compress, decreasing the volume in the system and causing an increase in pressure. Moreover, if the piston moves up, the volume of the system will increase, decreasing the pressure of the system. Work can be done on the gas by pressing in the piston downward. However, if an increase or decrease in pressure and or volume is desired, an external heat source or a cooling source from its surroundings must be added. A convenient way to visualize these changes in the pressure and volume is by using a pressure volume diagram or PV diagram. Thus, a PV diagram is a graph pressure as a function of volume. Each point on a PV diagram corresponds to a different state of the gas. The pressure is given in the vertical axis and the volume is given on the horizontal axis. So here is the example of PV diagram.
In this part of the discussion, I will discuss to you all about the four structures in the PV diagram shown in this module. So first off, I would like to know if you know what the formula for the internal energy is. Do you guys know? Chart. So the internal energy or the AU, triangle U, this is equal to the heat or Q minus W or the work. So this formula is used for the transfer of energy. So in this, when you have a higher, when you put heat in the container, you will have higher heat or higher internal energy as well as the work when put inside. So in the conservation of energy, you can say that you will have a higher conservation if you have higher heat pressure, temperature, or volume, it depends on the on what structure you use. It depends on that to have a higher internal energy. So the first structure is the isobaric process. This is where the pressure must stay the same as it was from the start. So in this, the gas are used in mechanisms such as stove, and as you add heat, the pressure increases. Yes, the pressure increases. So in this part of the discussion, I would like to discuss to you all about the structures used in the PV diagrams given in the module. So first off, I would like to know if you already know what the formula of getting the internal energy is. So what is it? Okay. Correct! So the formula in getting the internal energy is triangle U is equal to delta U is equal to Q minus W, or the heat minus the work given. So as an example for the isobaric process where the gas is held at constant pressure, imagine a cylinder filled with gas and the top of a movable piston that has a mass. At the start of the pressure is a certain amount the volume of gas involved. A heat source is added under the cylinder and slowly heats up. In an isobaric process, the pressure must stay the same as it was from the start. We expect what with the additional internal energy, the molecules will be bouncing around a bit more. The gas will do work against the piston as it expands, where W is equal to P, or the pressure, and the distance for the volume. So the formula for getting the work for the isobaric structure is writing the work is equal to P and the derivative of the volume. So if you're given two volumes, which is the volume from the first one and the final volume, you get W is equal to P times V2 minus V1, and you multiply that with given numbers, such as if you are given V2 is equal to 5 and V1 is equal to 3, cherva, and P is equal to 6, you get 6 times 5 minus 3 is equal to 6 minus 2 is equal to 12, and the unit for work is, what is the unit for work? That's my question for you. What is the unit for work? The second structure is the isochloric, or the gas is held at a constant volume. In an isobaric process, the gas must keep a constant volume, and imagine a sealed container that cannot change a shape as heat is added, and the gas will want to expand even though it can't. This will build up pressure inside the cylinder, and the increase in pressure will also create more force against the sides of the cylinder, but since nothing is moving, no work is done. So if you put pressure inside a volume, you can produce work, and you can say that work is done. So in getting the isochloric process, the work for the isochloric process, you need to use the W is equal to F D, where if you have no pressure put to it, you have 0 F, so F is equal to 0, and times D, where no distance is added, so your work is equal to 0. So in the first law, the thermodynamics shows that since no work being done or work is equal to 0 joules, all that heat being added up just increases the internal energy. So in the internal energy, you have delta U, or the internal energy, is equal to Q plus W is equal to Q with volume and W with none. So delta U is equal to Q because W is equal to 0. So only heat adds to the internal energy, giving the isochoric process difference, or difference from the first one, which is the isobaric process. So the third one is the isothermal process, and during this process, heat can enter and leave the gas, but the total energy in the gas will not change. Imagine a cylinder piston with a top and is filled with gas, and the cylinder is sitting inside a large container filled with water. If anything happens to the cylinder, that would normally cause a temperature change in the gas. The water will either absorb or release the heat to keep the gas in the cylinder at a constant temperature. We have been holding on the piston a bit, but now we release it so that the piston rises. The volume of the gas is expanding and the pressure inside will be dropping. Work is being done by the gas, so to keep the internal energy, the constant of the gas must be absorbing the heat from the water. As long as the energy is lost equals the heat gained from the water, the internal energy will not change and the temperature stays the same. So if you are given the internal energy U is equal to Q plus W, which is finding the internal energy, delta U is equal to negative W plus W, which is from the isothermal process given, because it will be the gas of it will be released, so the internal energy would be 0 because they have the same value. And the PV diagram we got shows the curved line and the pressure and the volume both change, and the line is called isotherm, which means the temperature stayed the same. The isotherm is a curve, and this happens because when a piston was being released, there was a sudden drop in the pressure of the gas expanded. As the process continued, the pressure dropped more slowly as the volume increased in the area. Where you can see, when you have the given volume, the lines of this would go like this. Yes, then this is 1 PV minus V1 in the first dot. The second will be P2 minus times V2. This is multiplying. Yes, where this is the pressure and this is the given velocity. So the last structure is the adiabatic process. An adiabatic process is a process in which no heat enters or leaves the system. In an adiabatic process, heat flow is 0. Applying the first law of thermodynamics, if the internal energy is equal to heat plus work and heat is 0, the change in internal energy of the gas must be equal to the work done on the gas. So if you need to get that, you write the formula. Internal energy is equal to Q minus the W, or the work, internal energy. If heat is equal to 0, so you have the W. So in this process, you have the only the work to get the internal energy for the adiabatic process. And if the gas is compressed, work is done when it is positive. If the gas expands, work by done is negative, the internal energy decreases. So it is vice versa. If you add pressure, P is equal to higher, you have you have an increase in your internal energy. But if you have lesser pressure, you have lesser also, or your internal energy will decrease. So the next reporter will discuss to you later on what the second law of thermodynamic is, and the next part of this discussion would be the work done by a gas.
Good morning everyone, this is Reishane Eltanal and I'm going to explain to you what is work done by gas. It is when a force acts upon an object to cause a displacement of the object. It is said that work was done upon the object. Work is defined as the energy it takes to move an object against the force. Work is one of the fundamental ways energy enters or leaves a system, and it has a unit of joules. Gases can do work through expansion or compression against a constant external pressure. Work done by gases is also sometimes called pressure volume. When the gas expands against the external pressure, the gas has to transfer some energy to the surroundings. Thus, the negative work decreases the overall energy of the gas. When gas is compressed, energy is transferred to the gas, so the energy of the gas increases due to positive work. The force of an expanding gas on the piston is equal to the pressure exerted by the gas multiplied by the area of the position. The work the gas does to move the piston to a certain distance, X is equal to W equals P A times delta X. But A times delta X is equal to the change of the volume A delta V of the gas. Hence, the formula is W equals P delta V. Here is the number 1 example.
This is how to solve work done by gas. First, you need to find the given. Next is use the formula when solving the problem. W equals P delta V. Here's another example.
So thank you guys for watching. That is how to solve work done by gas. Thank you.
Are reversible and irreversible processes. So, a thermodynamic process is said to be reversible if the process can be turned back such that both the system and the surroundings return to their original states with no other change anywhere else in the universe. So, whereas if the system and the surroundings do not return to their original condition once the process is initiated, it is an irreversible process. So taking an example of an automobile engine, so that has traveled a distance with the aid of fuel equal to an amount X during the process. So the fuel burns to provide energy to the engine. So converting itself into smoke and heat energy. So we cannot retrieve the energy lost by the fuel and cannot get back the original form. So in reality, no such processes as reversible processes can exist. So another example is a reversible process. So imagine you have a toy car, then that can go forward and backward perfectly without any problems. So you wind it up, it moves forward, and then you can wind it backward. So and it goes back to where it started. So everything is exactly the way it was before. So that's like a reversible process. You can go back and forth and nothing is changed permanently. Whilst the irreversible process, so example, so now you think about a regular toy car that only goes forward. So once it moves, it's done. So you can't wind it backward to make it go in reverse. So it's like an irreversible process because you can't undo what just happened. So yeah. While we talk about reversible processes in theory, in the real world, many processes are irreversible because some changes can't be undone.
In the second law of thermodynamics and entropy, the second law of thermodynamics is about the quality of energy. It states that as energy is transferred or transformed, more and more of it is wasted. The second law also states that there is a natural tendency of an isolated system to degenerate into a more disordered state. The state of disorder is called entropy. For instance, we can identify entropy by how disordered a space is, like a room after it is cleaned results in clutter everywhere. Let's identify entropy by observing a glass of crushed ice and a glass of water. You would say that a glass of ice has higher entropy because of how it looks like, how it is more messy than a glass of water with a stable surface. However, the latter has higher entropy than the former because the molecules of water, which is a liquid, has more freedom to move or to roam around, making the subject have higher entropy than a glass of crushed ice. So entropy can also be defined as a measure of a system's thermal energy per unit temperature that is unavailable for doing useful work. Because work is obtained from ordered molecular motion, the amount of entropy is also a measure of the molecular disorder or randomness of a system. The concept of entropy provides a deep insight into the direction of spontaneous change for many everyday phenomena. When a gas expands into a vacuum, its entropy increases because the increased volume allows for greater atomic or molecular disorder. The greater the number of atoms or molecules in the gas, the greater the disorder. The magnitude of the entropy of a system depends on the number of microscopic states or microstates associated with it. In this case, the number of atoms or molecules. That is, the greater the number of microstates, the greater the entropy. A disordered system has a greater number of possible microstates than does an ordered system, so it has a greater entropy. This is mostly clearly seen in the entropy changes that accompany phase transitions, such as solid to liquid or liquid to gas. As you know, a crystalline solid is composed of an ordered array of molecules, ions, or atoms that occupy fixed positions in a lattice, whereas the molecules in a liquid are free to move and tumble within the volume of the liquid. Molecules in a gas have even more freedom to move than those in a liquid. Pangit. Wala na. Each degree of motion increases in the number of available microstates, resulting in a higher entropy. Thus, the entropy of a system must increase during melting. Similarly, when a liquid is converted to a vapor, the greater freedom of motion of the molecules in a gas phase means that delta S sub VAP is greater than 0. Conversely, the reverse processes, condensing a vapor to form a liquid or freezing a liquid to form a solid, must be accompanied by a decrease in the entropy of the system. Entropy can be calculated by using the ratio of Q over T, and this ratio can be defined as a change in entropy delta S for a reversible process. For instance, we can identify entropy by how disordered a place is, like a room after it is cleaned results in clutter everywhere. Another example of entropy, but in this case let's identify it by observing a glass of crushed ice and a glass of water. You would say that the glass of crushed ice has higher entropy because how it looks like, how it is more messy than a glass of water with a stable surface. However, the latter has higher entropy than the former because the molecules of the water, which is a liquid, has more freedom to move or to roam around, making the subject have higher entropy than a glass of crushed ice. Entropy can also be defined as a measure of a system's thermal energy per unit temperature that is unavailable for doing useful work. Because work is obtained from ordered molecular motion, the amount of entropy is also a measure of the molecular disorder or randomness of a system. The concept of entropy provides deep insight in the direction of spontaneous change for many everyday phenomena. When a gas expands into a vacuum, its entropy increases because the increased volume allows for greater atomic or molecular disorder. The greater the number of atoms or molecules in the gas, the greater the disorder. The magnitude of the entropy of a system depends on the number of microscopic states or microstates associated with it. That is, the greater the number of microstates, the greater the entropy. A disordered system has a greater number of possible microstates than does an ordered system, so it has a higher entropy. This is mostly clearly seen in the entropy changes that accompany phase transitions, such as solid to liquid or liquid to gas. As you know, a crystalline solid is composed of an ordered array of molecules, ions, or atoms that occupy fixed positions in a lattice, whereas the molecules in a liquid are free to move and tumble within the volume of the liquid. Molecules in a gas have even more freedom to move than those in a liquid. Each degree of motion increases the number of avoidable microstates, resulting in a higher entropy. Thus, the entropy of a system must increase during melting. Similarly, when a liquid is converted into a vapor, the greater freedom of motion of the molecules in the gas phase means that delta S sub VAP or VAP is greater than 0. Conversely, the reverse process, condensing a vapor to form a liquid or freezing a liquid to form a solid, must be accompanied by a decrease in the entropy of the system. Entropy can be calculated by using the ratio of Q over T, and this ratio can be defined as the change in the entropy delta S of a reversible process. In the module, it mentions several equations that is related to thermodynamics, and each variable has its meanings, where Q is a heat transfer, which is a positive for heat transfer into a negative for heat transfer out, and T is the absolute temperature at which the reversible process takes place. Take note that the SI unit for entropy is joules over Kelvin. If you are going to calculate the changes of entropy in a reversible process, the total would be zero. However, for an irreversible process, change of entropy is always greater than zero.
Good morning everyone, my name is Shanwayne Fetalcorin and I am here to discuss the second law of thermodynamics and entropy. First, I will show you a background about thermodynamics. Thermodynamics is the quality of energy, which it can be said as an energy is transferred or transformed. Here, I will give you an example about a problem of a reservoir. Then, the problem goes this way. Calculate the total change in entropy if 4,000 joules of heat transfer occurs from a hot reservoir at T is equivalent to 600 Kelvin is 327 degrees Celsius at a cold reservoir at T is equal to 250 Kelvin is equivalent to negative 23 Celsius, assuming there is no temperature change in either reservoir. Then, the formula that we are going to use this is delta S is equal to Q over T, which we are going to use to solve the problem. Then, as we solve the problem, first we need to find the heat. The heat formula is delta S is equivalent to negative Q heat over T heat. So, the problem is here. Then, this is the given 400,000 joules over 600 joules is equal to negative 6.67 joules per Kelvin. Now, and the next thing we have to do is we need to find the Celsius to find the Celsius, which we are going to use delta S is equal to Q Celsius over T Celsius, which we are still using the 400 joules over 250 Kelvin, which is equivalent to 6.0 joules per Kelvin. Then the last steps we are going to find is the delta S is equal to delta S heat plus delta S Celsius. This formula is to calculate the total change of entropy. In finding the two change in entropy, we are going to use 0.67 joules per Kelvin plus 16 joules per Kelvin is equal to 9.33 joules per Kelvin. So there is an increase in entropy of the system of two heat reservoirs undergoing this irreversible heat transfer. This means there is a loss of ability to do work with this transformed energy. Entropy has increased and energy has become unavailable to do work.